할게. 그 문장 어떻게 바꾸는지 봐봐. 할 Hi, I'm going to give you a brief presentation on NUDD of the NAP designing process. NUDD stands for New, Unique, Difference, and Difficulty. So there are 10 main topics in this presentation, and the whole thing will take about 40 to 50 minutes. Feel free to ask questions whenever you have any question. The first thing I want to talk about is the content of this presentation. I'm going to be talking about subsections like DIA, TIA, DFM, and FMEA, and then we will get to NUDD of the NAP designing process. So you have all these acronyms. The DIA is Design Input Activity, which is subpart of the designing process, and you have TIA, which means Test Input Activity. And you have DFM, Design for Manufacturing, and FMEA means Failure Mode and Effect Analysis. So I'm going to be talking about all those, and this chart in your PowerPoint slide shows how we at SK Hynix designs a new product. Upon the completion of phase 4, we get the design targets, and all those design targets are summarized as speed, current, and net die. And then we get to the designing process to meet the requirements, or you can call them the design targets. So after the preliminary designing process, we do a presentation, and that is called the pre-design review. In this review, the design steering committee is formed, and in the designing steering committee, there are senior engineers, and they check on the basic functions and features and try to see if there's any weaknesses and malfunctions. So after collecting all those feedback from the review, you get to work on those review and work on improving the circuits. And the next, you have the final design review. In the final design review, you check on whether all the feedback has been reflected in the actual process, and you do the final checkup. Once everything is approved and everything's good and proven to be good in the final designing process, the designing process is finally completed. So after the designing process, the next is verification. In the verification stage, you get actual physical wafers, and you check on whether the wafer does all of the jobs, all of the basic functions, and all the features. You try to see all the actual features that actually work without problems or glitches. You also check on whether the new features work fine. So you repeat the checkup and the improvement process. All of these are part of the verification process. So you have DIA, Design Input Activity. DIA is a call for action from other participating teams. So you have the design team, and you have all other participating teams. And then these teams give you DIA. So DIA is like a call for action. You need to do something, design team. So that's DIA. So DIA comes from other teams on what to improve on. These teams are product team, application team, device team, and the QA team, quality assurance team. And all of these participating teams ask the design team to change something. So when there's some problem or some glitch, other teams call the design team and ask them to do something about that. By receiving DIA from all these participating teams, the design team improved the reliability, yield, and lessons of the previous versions of devices. So now we have the NAP, and before HUMA. So now we have the NAP, and before then there's Polaris and there's HUMA. And before HUMA Tech, DIA took place during and in the middle of the designing process itself. And that caused a lot of confusion and tedious and ineffective communication, because you have DIAs like while you're doing the designing process. So you got to fix something, and you're designing, and you fix something, and then you go back to the previous problem. So that was all those, there was all those confusion and ineffective communication. Now after HUMA Tech, all of the DIAs come before the designing process. So if DIAs come in between the various stages of the designing process, you can see you need to change the designs like I explained. So that's a lot of confusion. By putting the whole DIA calls at the very initial stage of phase 5, we don't have to worry about this problem anymore. So this table shows, in your PowerPoint slide, this table shows DIAs are now collected and managed seamlessly across various versions. For example, the NAP's DIA already includes those of Polaris and Humatech. Therefore, the NAP includes Smart Refresh or eFuse. By doing this, we can only improve the stability and reliability of DRAMs made by SK Hynix. And this is an example of a DIA list that you have that in your slides. Each item talks about the purpose and effect of a given change, which the design team considers and reflects on the actual circuit. So when you develop one new device, the whole process is categorized from phase 0 to phase 10. So it's called the device planning stage. From phase 0 through phase 4. So that's device planning stage. And phase 5 is a designing process. Phase 6 and phase 7 is the engineering sample process. And the customer sample process is from phase 8 through phase 9. Upon the completion of phase 4, you get the targets or goals like the speed, current, net die, yield, and reliability. Each department and team comes up with appropriate actions in order to meet all those targets and requirements, and tells the design team what to do to improve all that. DIAs are the items that you need to improve in order to meet all these targets. And next is a TIA. So you have the DIA, and TIA is test input activity, which is an opposite, a reverse flow of DIA. So the TIA is a checklist that the design team gives back to other participating teams. So again, DIA is from other participating teams to the design team, and TIA is from the design team to other participating teams. And again, other participating teams are product test team, application test team, or the device team. TIA is a verification process to check on whether all of the design changes actually do work well on the actual circuit. So TIA therefore includes all of DIAs, because DIA was a calls for action by the design team, right? So design team work on that, and TIA is actually verifying whether all those changes have been made and actually they work just fine. So next slide, here's the examples of TIA. This TIA mentions the purpose and effects of each item, changes on the circuit, the test pattern, to verify these changes and expected results. All these items, all these things are in a single TIA. Next is design for manufacturing. Design for manufacturing is a methodology used to design the circuit. So the circuit can embrace sufficient margins for PVT variations. So you have PVT. PVT means process, voltage, and temperatures. And all these things change and varies, and they differ in different circumstances. And when there's an irregularity, let's say there's an irregular voltage input to the circuit, so it goes up and down, and there's irregularity, or the temperatures could be out of the normal range. So it could be way too high or way too low. But still, the circuit has to work just fine. So how do you guarantee this? How do you guarantee that the circuit works just fine among these irregularities? We put Gaussian typed, so you have Gaussian curve, Gaussian typed variations of process voltage or temperature into a simulation. So you have a software that simulates all these functions and try to see if the board still works just fine. By simulating hundreds of or thousands of cases of irregularities, we get to design a robust circuit that endures all these PVT variations. So DFM is a process, and you use this process to guarantee the functionality of analog-based as opposed to digital, analog-based circuits like IO sense amplifier. Next is failure mode and effect analysis. So all the failure reports are managed by the intranet, and you have intranet. within the SK Hynix organization, and all these are shared by all the engineers and all the appropriate personnel in design, device, product, and application teams. When a failure happens in the verification stage, and everything is recorded on the online intranet system so that you can share it. So during the course of development, all of these items regarding failure and amendments are recorded item by item and saved online. So you have this database. So for hundreds of devices that we have developed in the past, you have all these glitches and failures and how we mended all those problems. We have all those information in our database. So in the designing process, we make the most of this database. So we check on the database and see if there was the same problem in the past, and we check on those failures and whether we have solution to that problem. If we already have the solution, then you use it. If we don't, then you go out and do something about this. So in the verification process, the test engineers look at the past failure histories in the database for the same type of failures and use this thing to take care of the new problem. So this FMEA system, you need that to design robust circuits. And to give you an idea on this process, there's about 4% change in the NAV tag compared to the previous Polaris version. And there has been no change in the specifications of DDR3 for the past couple years. And now the trend is turning to DDR4 from DDR3. And these 4% changes are like the ones on NUDD, including the solutions to the row hammering and PPR using eFuse. Last but not least, I'm going to talk about the NUDD review, new uniqueness, differences review of the NAB. So there are 4 subtopics under NUDD. You have Smart Refresh, which is a solution to row hammering problem. And you have sensing margin problem. And sensing margin is a solution to cold TWR, time for writing. And you have pre-trimming, which is a solution for the protecting under-screening or over-screening. And we also made changes to the architecture to improve low VDD and accomplish higher speeds and improve on the power mesh. First, Smart Refresh. Smart Refresh is a solution to row hammering problem. It has been discovered by Google back in 2014, and SK Hynix, we already knew about that before Google. And we tried to find a solution. Starting from HUMA 4 gig DDR4, SK Hynix applied Smart Refresh. But the problem was, after HUMA 4G DDR4, the tech migration took place. And then you have better technology, and everything has got smaller and smaller. So we have worse row hammering problems. So to figure out this problem and to take care of this problem, we further improved the algorithm of Smart Refresh in the NAP version. So let me briefly explain the row hammering phenomena. Row hammering takes place. So you have a given row, and when it's accessed multiple times, way too frequently, the rows immediately neighboring the given row tend to lose data. So you have a given row, and right above that row and right below that row may lose data. What happens is that the given row that you have, which is accessed way too frequently, it kind of keeps hammering on the neighboring rows. So the one above and the one below, the given row keeps hammering both of them. So the neighboring rows tend to lose data, and this is a problem. You lose data, which is not good. So how does Smart Refresh takes care of this problem? Smart Refresh algorithm has 3 parts. You have detection stage, calculation stage, and execution. So in detection, the Smart Refresh circuit monitors the address, which is active, right? So you have the row that kind of keeps hammering, and you have the address of the row, right? And you save that address. Let's call it address N. So address N is a row that is being accessed too frequently. So its neighboring rows may lose data because the address N can keep hammering its neighboring rows. So second in calculation, you take n minus 1. So n is a given row, so n minus 1 and n plus 1 to figure out what the neighboring rows that are now at the risk. So you have the addresses of the neighboring rows. The third in execution, DRAM smart refresh the rows at n minus 1 and n plus 1. So what it does is that it rewrites and it strengthens the data in those neighboring rows at n minus 1 and n plus 1. We do that at the next refresh timing. So in the NAB, we found that row hammering affects 4 rows instead of 2 rows. So before you had row hammering in 2 neighboring rows. In the NAB, we figured that the given row hammers not just the one above and the one below, 2 rows above and 2 rows below. So you have 4 rows that are at the risk, which is a problem. So what we did was the NAB kind of calculates and remembers also n minus 2 and n plus 2. So the rows at n minus n plus 1 are more likely to lose data because it's immediate neighbors. And then the ones at n minus 2 and n plus 2, they're also risky. They can lose data. So the NAB remembers all those 4 neighboring rows and then kind of smart refreshes all of them. So we tested the system and we figured that there's no problem. And the conclusion is SK Hynix, the NAB is free from the row hammering phenomenon. 여기까지만 해?
아니 좋아.
다 해?
계속해.
다 해? Okay.
야.
Okay, next is the sensing timing control for code time for writing, TWR. So silicon activities differ in both MOS FET structure. In other words, the electrons move passionately in high temperatures. So if you have a high temperature, you can imagine the electrons just moving faster and faster. And the movement to slow down in lower temperatures. In high temperatures, the system writes the data more efficiently on the DRAM cells, right? Imagine it's high, like it's boiling, right? It's writing like faster and like more efficiently. So it requires a shorter TWR. But it does not keep the data well because it's high temperature, it easily evaporates. So you lose the data easily, but at the same time you write better and faster. On the other hand, in low temperatures, you can imagine something like something that's like in a fridge. It's cold, right? It's hard to write on that. And the system does not write the data as efficiently, which requires a longer TWR. But it saves the data more easily because imagine like hard surface that's in a fridge. It's hard to write it, but just right there, it stays there a longer time. So this is why we have more of the TWR problem in low temperatures because it takes longer to write on the cells. So in order to improve on solve this problem, in the NAB, we control the sensing time by measuring the ambient temperature around those DRAM cells. So in low temperatures, what we do is that it makes the sensing time longer because the recorded TDR is longer. In high temperatures, on the other hand, the NAB makes the sensing time shorter because the recorded TWR is shorter. So it's simple. Longer, longer, and shorter, shorter. So this slide, in your PowerPoint file, shows the RCD data, reading data, which tells you that this mechanism actually works well. In all ranges of temperatures, our device passes the margin test, which is fantastic. Next, preventing overscreening and underscreening by using pre-trimming. So when wafer are fabbed out, you have a brand new wafer. Each DRAM chip has different biases due to variations of the manufacturing process. So you have a different machine, you have a different results. Trimming compensates and adjusts these biases by compensating and adjusting each chip's activities. So we used to use trimming, but previously the trimming was done before the package test. So that's what we did in the past, but in the current test sequence, we do the pre-trimming and then go on to the wafer test and package test. We do the pre-trimming and then wafer test and package test. So we prevent under screening